So good morning or good afternoon, depending on where you're connecting from. Today, we have the great pleasure to have with us Luca dal Zilio from ETH Zurich, and he's going to tell us about a place which everyone is finding amazing, which is the Himalayan Thrust. So Luca, the floor is yours.
Thank you very much, Catherine. It's a great pleasure to present these results today. So thank you for inviting me to give this talk. With this presentation, I would like to discuss the Main Himalayan Thrust. And in particular, I would like to discuss the elastic energy storage related to earthquakes, small and large earthquakes in this context, and the lateral segmentation. And of course, I would like also to thank the people that have been involved with me in this past 4 to 5 years, and thank them for the work we have been done so far. And I'm happy to share it with you today. So we know that the Himalaya is a result of the convergence and collision between India and the Eurasiatic plate over the last 65 millions of years. The convergence occurred at the plate rate that was significantly high during the subduction process, and is still nowadays quite high. So if you look at GPS stations at the surface of this mountain range, we can see kind of a snapshot of this convergence rate, and we can see that the slip rate on the fault is still significantly high. Most of this slip is actually accumulated along the plate boundary, along the interface between India plate and the Eurasiatic plate, which is the Main Himalayan Thrust. So the Main Himalayan Thrust is the equivalent of the megathrust in a subduction zone, and is the place where we can observe also most of the large earthquakes in this region. In fact, if you look at the historical seismicity distributed across the arc, we have a catalog of moderate to very large events with magnitude that are higher than 8, and with other events, partial and complete ruptures of magnitude 7 up to more than 8. And so this region is pose a significant seismic hazard, also because it's located in a region where the population density is significantly high. Now, when we look at the reason behind the generation of these large earthquakes, we can see this very simple animation, which shows the convergence of India plate beneath the Eurasiatic plate, where here we have the accretionary wedge and the building of the Himalaya. And in black here, you can see the location of what we call this Main Himalayan Thrust fault, which is a fault that is in a length is approximately along 100 kilometers along depth. And with these 100 kilometers, I refer to the regions where we have the seismogenic zone, where we have events that they can propagate all the way up to the surface. And so when we look at this animation, you can see that the frontal part here, it's actually locked during the interseismic period and then we have a region that is creeping. And below here, at the transition between the locked portion and the creeping part, we have the building of the stress, and most of the earthquakes nucleate in this region and they propagate up deep. Some of them, they go all the way up to the surface, while some others, they tend to be confined in the lower part of this seismogenic zone. So when we think about the building of the Himalaya and looking at the scales of this problem, and here you can see an example of the time scales that are involved into this process. We can see that the propagation of an earthquake can generate a rupture that occurs within a few seconds, and we can have the nucleation process of an earthquake and other processes such as foreshocks, aftershocks, and post-seismic relaxation or after sleep after an event, which can occur with longer timescales. And at even longer timescales, we can see that there is a viscous relaxation that can occur within much longer timescales. And so you can see that here we have a spectrum of temporal scales that they can range from seconds all the way up to thousands of years or even millions of years. And so when we think about the building of a mountain range, we have to consider that these long-term tectonic processes are affecting the key ingredients that controls the nucleation and the propagation of earthquakes. And this could be the rheology, the fault geometry, and the bulk properties. And in the same way, these seismic rupture are over several seismic cycles, they can then affect the evolution of these tectonic features. So when we think about the building of a mountain range, and specifically in this case of the Himalaya, we have to consider of a process that is occurring over very broad temporal scales and also, of course, spatial scales. One way to determine the stress buildup between large earthquakes is by looking at the displacement at the surface and try to measure what we call the interseismic coupling. And so with this presentation of today, I would like to start by discussing how we can take GPS stations from the surface and try to measure the coupling distribution across the fault. And so when we try to do that, we have to assume that we have a certain long-term slip rate on the fault, and this is accumulated interseismically. So during this period of quiescence between events, slip rate is accumulated on the fault, and eventually this slip is released during an earthquake in the opposite direction. And so here you can see an example of a plate boundary where we have the regions that is interseismically locked, and then we have a region where it is basically creeping over time. And so this seismogenic zone shows that we can have a coupling that is between 0 to 1, and this defines the ratio between the interseismic slip deficit and the long-term slip rate. And so when the ratio between the two is 1, it means that the fault is interseismically locked. And so we can accumulate slip deficit on the fault that is eventually released by earthquakes. And can I ask the audience to mute themselves, because I can hear something in the background?
Yeah.
Okay, so so when we consider this interseismic coupling, we can assume that the coupling is 1 when the fault is interseismically locked, and is 0 when the fault is fully creeping, as we can see here in the blue part. And so now when we try to consider this problem as an inverse problem, we can do that in a Bayesian approach. So for those that are not familiar with this, for a Bayesian approach, I mean that we can measure this interseismic coupling, but everything that we define is in terms of probability. And so the way to do that is by assuming this classic case of an inverse problem. And we can assume that we have certain observations, which in this case are GPS and leveling data. And then we have Green's function, which is the Green's function computed for an infinite elastic medium by assuming a certain velocity model of our structure of the upper crust, lower crust, and lithospheric mantle. And then we have the model parameters M. So with this Bayesian approach, we can basically try to sample the posteriors of this probability density function by running several models. In this particular example is more than hundreds of thousands of models. And from there, we can get the distribution of coupling in terms of the probability of that. And so when we do that, we also try to constrain the misfit covariance matrix, which defines the data and also the prediction uncertainties that we have in there. So this is something that we can incorporate in this Bayesian framework. Now, when I mean the type of elastic structure, we know that we have some regional models, and in literature you can find different regional models. Here is an example with a dashed line of different publications with different regional models for Nepal. And you can see that we have this stratification of the P wave velocity, the S wave velocity, and density, and each model has some variability in there. Now, when we try to consider the Bayesian method, we try to consider a model that is the one in black, for example, within a certain standard deviation that is highlighted here in gray. So the method can take into account a certain level of uncertainties that we have in this case of the velocity model. So from there, we try to use some of the data that are available, and they have been already used in previous studies. And we have data of the GPS from the entire arc. Of course, in this case, you have to assume that the arc is very large and long along the strike. So the distribution of GPS stations, it's always kind of an issue, because having a good coverage of the entire region, it's always very challenging. And so later I will show you some of these results where you can see that some of the good constraints we have, they strongly depends on where these GPS stations are located. In this case, you can see that we have the main frontal thrust, which is the surface line of the main Himalayan thrust fault. And then we have also this distribution of the GPS. The different colors here want to highlight that the model has been divided in different blocks. So with these different blocks in this color, you can see along the strike the different portions of the fault. And then with this light blue, you can see the GPS stations within India plate.
Could you please mute yourself, please? Thank you.
And here you can see that in red, we have another regions that we try to consider in this model, which is the Shillong block. This region, for who is not familiar with this Himalayan region, is a place where they observe an internal deformation of the India plate. So we have to consider this part of the system as a separate compared to the GPS stations within the main Himalayan thrust. Now, when we try to run this inverse problem in a Bayesian framework, here you can see the results of the coupling distribution. So the coupling distribution shows the map on the fault of the different coupling degree from 0 to 1. And the black and the blue line shows the observed and the predicted model, which seems to kind of show quite a good agreement between the two, at least overall, we find a good agreement. What is interesting to see from this map is that when you see the distribution of coupling, we have that there are regions between red to black where the coupling is very high, so of 1, which means that the coupling is 100%. And the regions where it tends to go towards yellow and orange, as you can see here in this region and here, and again in this part of the fault. So you can see that there is a certain variability of coupling along the strike, while we have some other regions like this one and this region where the coupling is significantly high. And so there is a lateral variation across the arc. So these results are by using 10% of data uncertainties, and we try to run 280,000 models. And what you see here is the mean model of these 280,000 models. So they represent what we call it the posterior mean of coupling. The interesting part about using this Bayesian framework is that we can specifically look at each point on the fault and look at the probability density distribution. So here you can see an example of the same map distribution. Here you can see actually the color map, which shows the coupling between 0 to 1. And now we can take some points along the fault, here these white points, and we can look at the coupling distribution. So for example, if you take a point 2, you can see that the coupling distribution shows a very clear distribution of high coupling with very high probability for a coupling of 1. And similarly, we also have a very good high probability of coupling for this 0.4, and similarly also for 0.6. And this is just an example to show you that when we look at some of these points, we can look at how strong and how informative are the data for the coupling distribution. Now, if you try to instead look at 0.1, 3, and 5, you can see that for 0.1, we have a low coupling distribution, and the probability is still significantly high. And when we look at the distribution instead of 0.3, you can see that the distribution tends to be kind of flat between the coupling 1, which would be completely black or red to black, to a coupling that is 0. So this is just an example to show you that, for example, 0.3 is not well constrained, and the data we have in the region around this place are not very informative to constrain this point properly. When we look at 0.5 instead, we have a much better distribution because the probability for high coupling between 0.5 to 1 seems to be quite low. But when we look at the distribution for high coupling, that seems to be much higher. And so in this way, we can really see how informative are the data and how well are these points constrained spatially. After obtaining this coupling distribution, we try to look at the distribution of tectonic features and structural feature that can find any sort of a correlation between our coupling distribution, which represents kind of a present-day snapshot, with the tectonic features developed over millions of years of evolution. What we found very interesting is that this low coupling region do not coincide with any specific structure within the orogenic wedge, but instead they seems to correlate with some of the features that we can observe in the India plate. These gray regions here that you can see here are what we call it some ancient ridges. These ridges have been created much earlier than the Himalayan origin, and they represent a failed rift attempt within India plate in the past. And these are inherited structures that are now subducted beneath the Himalaya, and they seems to coincide with the regions where we have low coupling. So now when we try to compare the distribution of this region, we can then try to compare the distribution of coupling, the historical seismicity, and the present day microseismicity. So in this plot on top, you can see that we have the coupling distribution along the strike, and you can see that there is a certain variability between 0 to 1. And you can see that the coupling is changing spatially along the strike. And it's interesting to see that we have these low regions of coupling that it seems to coincide with the regions of these ancient ridges. When we look at the seismicity, in particular large events across the Himalaya, we have to first of all consider that there are important uncertainties in the along strike propagation of these events. This could be related, for example, to the event on 1505, which apparently was a magnitude larger than 8. We still don't know exactly how large was the event along the strike. But in general, we can see that most of these events seems to not fall within this region, or at least they seems to stop close to these places. So the question is whether these structures are indeed stopping the lateral propagation of these large events. And here is just an example of large events, but we can also look at small events from the present day seismic catalog, and then try to simply try to plot the cumulative moment released over time within this period of the catalog, and see how they spatially correlate with the structure. And it seems that these two regions are actually with a moment release that it seems to be quite low, at least compared to other regions. So By looking at this different data set, it seems that there might be some correlation between the coupling distribution, the distribution of seismicity, and the tectonic structures that we can see from geological fieldwork. Another type of data that we can use and compare with this coupling distribution is the arc parallel topography anomalies. Again, for those that are not familiar, this color map that you see represents the difference, so the anomalies, positive and negative anomalies, compared to the average profile to the across the arc. So you have to imagine that you have this region, you can take all the profile across the arc, obtain the average profile, and then try to compare it spatially with the locations of with the different topography spatially. And what you can get is regions where the topography is higher than average or lower than average. This has already been proposed in the past by Song and Simons in 2003, in particular for subduction zone, because this can kind of give us some clue on how is the distribution of coupling compared to the regions where the topography is maybe subsiding interseismically because we are accumulating strain. And this could be in the preparatory phase between large earthquakes. And on the other hand, it seems that the positive anomalies of the topography distribution seems to correlate with the regions where the fault is instead creeping. So where we have a steady creep over time, and we don't accumulate a significant strain to propagate large earthquakes. So in this map, you can also see the location of where the coupling is 0.1, so of 50%. And you can see that these low coupling regions, they coincide with the regions where we have these ridges. The most important point of this figure is that this region seems to correlate also with a positive anomaly, topography anomaly. So you can see that we have regions where the coupling is significantly high, like in this region, and in this one where then we have a negative topography anomaly, while in these regions and here we instead have positive anomalies. Of course, you can see that there are some uncertainties in this distribution, but in general, this can kind of give us some constraint of the correlation between coupling and topography expression. So what did we learn from this type of results? First of all, by using a stochastic model in a Bayesian framework, we can obtain a distribution that is more consistent and can give us a better idea of the probability distribution, not only the absolute value of this coupling, but also how good are these data spatially. This is to some degree in contrast with the previously published coupling map, where they don't observe any spatial variations. But in our case, we don't impose any smoothing regularization. So the coupling that you see here is not a result of any smoothing regularization. And when we do that, we see this heterogeneous distribution of coupling. And another important point is that this homogeneous coupling, more similar to previous studies, more of a coupling that is homogeneous along the strike, is obtained when we have a strong assumption in our inverse problem. So when we assume that the coupling is 1 in regions where the data are very poorly constrained, this is not probably the most ideal condition to obtain a coupling distribution that is consistent with the data we have available. However, when we relax these conditions, we tend to observe a more heterogeneous distribution. From this distribution, you can see that the coupling is high and low in some parts, and it seems to kind of highlight some sort of segmentation within the arc, which could affect the lateral propagation of large events. The uncertainties are still significantly high on this, but in general, so far, this coupling distribution seems to correlate quite well with the distribution of different earthquakes in the past. The question is whether this potential barriers along the strike could prevent the propagation of very large earthquakes. And in general, we also observe that the coupling is significantly high, and there is a very small percentage of inelastic deformation, which we think is of the order of 10%. Now, when we look at more specifically on earthquakes in the Himalaya, probably the best example we can use is the more recent 2015 magnitude 7.8 Gorkha earthquake. Here you can see the map of the co-seismic slip distribution of this event, which happened in a region where we knew that the coupling is significantly high. The interesting features is that the event propagated along the strike for 140 kilometers, but it didn't propagate all the way to the surface. So for that, we call it a partial rupture of the Himalayan megathrust, of the Main Himalayan Thrust fault. Now, when we look at the distribution of seismicity, as I previously mentioned, this distribution is very variable along the strike. From historical seismicity, some of these events clearly reach the surface, and there are indications from trenches that have been made at the main frontal thrust. But many of these other events seems to be confined in the deeper region of the fault. So we have this magnitude 7 plus earthquakes in the deeper part of the fault, and very large events that instead propagate all the way to the surface. So it's still not very clear what are the conditions that allow to propagate this relatively moderate to very large earthquakes. So after the Gorkha earthquake, many studies have been published, particularly to provide also some constraint on the fault geometry and the correlation between co-seismic slip and the fault geometry. Here is just an example from the cross-section provided in Elliott et al. 2016, where you can see the cross-section and the location of the Gorkha earthquake, which happened in the deeper part of the fault, and more specifically in part of the décollement, in this more sub-horizontal part of the fault, and in this part of the fault where it gets steeper. And this part of the fault is also well known as a mid-crustal ramp. So in this case, you can see that the fault seems to be sub-horizontal in the deeper part. Then we have this mid-crustal ramp and this sub-horizontal décollement. And the distribution of the seismogenic zone seems to be located roughly from the front all the way to the end of the mid-crustal ramp. So because of that, the event has been considered as a partial rupture. However, when we look at this event and we try to then understand how we can use numerical simulations to understand the seismicity of this region, one of the key questions is how we can use this existing and new geologic, geodetic, and laboratory, and also seismic data in numerical experiments, and try to inform these numerical experiments such that we can have a better constraint on the initial conditions of fault geometry, temperature, structure, rheological parameters, and seismic data. So to do that, we decided to develop a new tectonic and earthquake cycle models, which we call it here VEL2 cycles. Is a viscoelasto 2D cycles of earthquakes, is a 2D model in a finite difference, where we can solve the fundamental equations of conservation of mass, momentum, and heat. And an important ingredient in this equation that you see here is that in the momentum equations, when we take into account the stress distribution and the pressure distribution in the domain, we also take into account the derivative of the velocity over time and multiply density. This is what we call it the inertial term. And when we try to simulate a dynamic rupture that propagate at kilometer per second rupture speed, it's an important ingredient to consider when we try to simulate this type of events, and also to propagate seismic waves. I'm sorry, is there any question?
No, I think it's a problem of someone unmuting himself.
Okay. So in that case, I continue. And another important ingredient in this type of simulations is that we try to consider also not only the elastic component, which is typically assumed for slip inversions and simple seismic cycle simulations, but also try to consider the viscous and the plastic component of the formation. So in this case, we assume a Maxwell viscoelastoplastic model where we have in series this three component of elastic, viscous, and plastic component. So finally, another important aspect that we have to consider when we try to simulate long phases of interseismic deformation and then a coseismic phase of dynamic rupture is by including the evolution of friction. So friction is not a constant parameter, but it evolves with the slip rate, with the sliding velocity. And so when we do that, we can assume different friction laws. Probably the most well-known friction law is rate and state dependent friction. So here you can see that shear stress is a function of friction and the effective normal stress. So when we expand this term F, we can obtain this equation where we have a reference friction, and then we have these A and B parameters, which are parameters derived from the lab. And then we have the ratio between the logarithmic of V over a reference velocity. So this is the sliding velocity. And then we have this theta, which is a state variable, divided by a certain characteristic slip weakening distance. Now, when we look at the distribution of the shear stress with the displacement, rate and state looks like this. So when we have a certain steady state value of shear stress and we try to accelerate the fold will initially re-strengthen and then it will follow a phase of weakening. This re-strengthening phase is controlled by the parameter A that you can see in the equation, and the evolutionary effect, where we reach a new steady state value, is controlled by the parameter B over a certain critical distance, which is the RS. In this case, A minus B is negative, and so the material is considered to be velocity weakening. It means that we can generate a frictional instability, and so the material allows the fall to accelerate all the way up to a meter per second slip rate. Another important constraint on this type of simulations is to use the rheology, geometry, and the temperature distribution consistent with the information that we have from the Himalaya. So here you can see a model that tends to represent the conditions that we have from the study of Elliott et al. In 2016, but we also try to create other models that it seems to fit better with other publications. In this case, we have a more of a smooth ramp distribution here. So the model looks kind of similar, but you can see that the ramp here in the frontal part and the mid-crostal ramp are more smooth. And finally, just for comparison between the two results and really try to understand the difference between them, we also trying to run some simulations where we instead applied a planar fault all the way to the regions where we have this transition from the more brittle to the ductile transition of the fault. Another important constraint is also the temperature. So temperature really affects this material, the rheology of these rocks. And so this is an important constraint that we need to consider for the internal deformation of the wedge and also for the sliding velocity, for the sliding behavior of the fault, from the more brittle in the shallower part to the more ductile in the deeper portion of the fault. So here you can see the temperature distribution within the entire domain. However, the regions where we run seismic cycle are basically a small part of this domain, which you can see here in this plot, where in gray you have the distribution of the of rocks, and in red you can see the isotherms of temperature. And so you can see that the temperature changes very quickly from 100 degrees all the way to roughly 400 degrees roughly at the end of this mid-crostal ramp. So we try to incorporate the temperature distribution more in the entire domain, and also the temperature distribution specifically within the wedge, such that we can have an initial good conditions for these seismic cycle simulations. An important part of these models is trying to constrain the surface deformation that we can have from GPS stations and leveling data with the strain distribution within the wedge. And so here you can see the velocity at the surface, and these bars here, the blue bars represents the horizontal deformation, while the pink, the purple bars represent the vertical uplift from the leveling data. So the solid line that you can see here represents the surface deformation from the horizontal and the vertical component from this model that you can see below here. So you can see that we can match quite well the distribution of horizontal and vertical displacement. And when we look at the distribution of strain, which is this color map, in particular the elastic strain, you can see that most of the strain is localizing on the fault, and then also within the wedge, particularly in this frontal part of the wedge, where we have the transition from the décollement to the mid-crostal ramp. The blue lines that you can see here is the distribution of the compressive axis. So it shows the orientation of the compressive axis. In this region, we have the axis is sub-horizontal, so we are in a pure compressive domain because the axis is indeed horizontal. However, here you can see that the axis becomes subvertical. And this is because the temperature here gets very high, and because of the topographic load, the vertical stress becomes dominant in this case. So because of that, we can use this type of simulation to kind of calibrate the initial conditions before running seismic cycle simulations. Now, when I look at the distribution of rupture events over several seismic cycles, here you can see the distribution of ruptures on the fault. So here you can see a plot where we have the distribution of what we call it partial ruptures. So each of these red lines represent an earthquake that is happening in the deeper part of the fault, and the black circle represents the hypocenter of these events. So you can see that most of these events are actually propagating in the deeper part of the fault, and then after 3 to 4 events, we have the propagation of the larger event all the way to the surface. So this model shows that we have sequences of partial ruptures, which are then followed by complete rupture, as you can see in this case, and here and here. So we have a sequence of roughly 2 to 3, up to sometimes 4 events. And then eventually we have the large event that propagates all the way to the surface. So this is just an example of this type of simulations where you can see that most of the events are indeed nucleating very close to the mid-crostal ramp. So when we look at the distribution of the length of this event and the magnitude of them, you can see that these events, they tend to be more like a Gorka earthquake when they are confined in the deeper part, and we have ruptures of the order of 40 to 50 kilometers long, sometimes 60 kilometers long along deep. And then we have the largest event, which they saturated the entire length of the fault, which is roughly of 100 kilometers. So we continuously switch between events that are roughly of a magnitude 7.5, 7.8 to magnitude that are roughly 8.4, 8.5. So the reason behind this type of behavior is strongly dependent on the stress distribution on the fault. When we look at the distribution of the stress and the yield strength, as you can see here along the fault from the frontal part to the deeper part, you can see that typically because of the presence of this mid-crostal ramp, stress is highly localizing in the deeper part of the fault, which leaves a very high, very large difference between the stress and the strength. And when an earthquake nucleates in this part where stress is getting very high, we have that this difference between the stress and the strength will prevent rupture to propagate all the way to the surface. So we have a partial rupture of the fault. However, when we nucleate several of these events, we tend to increase also the stress in this deeper part. And so we reach the condition where the stress distribution is high all the way from the surface to the deeper part of the fault. So the strength difference, which is this gray area separating the two lines, is getting smaller and smaller. And when this is the case, we can then nucleate the next event, and then this event can propagate all the way to the surface. And here is the distribution of stress after a complete rupture. And when this happens, we then restart with a new cycle of event. So because of that, we typically try to refer to this as a super cycle, because we have cycles of partial ruptures, and these partial rupture are creating the conditions for having the large event. And then eventually this complete rupture reset the stress condition within the fault. Before I was talking about this bimodal distribution between partial and complete rupture. The best way to represent this sort of like separation between a partial and complete rupture is by looking at what we call it the S parameter. The S parameter represents the average strength excess, which is this gray region that you have seen before between the two, the black and the red line, and the stress drop caused by the earthquake. So when the S parameter is high, we tend to have partial ruptures. And this is because the stress drop is lower than the strength excess. However, when we have a complete rupture, this ratio tends to get closer and closer to 1. So here you can see that when we assume the fault geometry with a clear mid-crustal ramp, we have a distribution of this partial rupture where we have the down dip width of roughly 40 to 60 kilometers, and the S parameter is between 3 to 8 up to 9. And then we have a gap in the length, and then we have this complete rupture. This is what we mean with bimodal distribution of seismicity. And this is also something that we observe very clearly also in the model where we have this smooth ramp, which clearly shows that the mid-crustal ramp is a very important ingredient in the model in order to obtain this type of behavior. However, when we assume a planar fault geometry, it's interesting to see that we have a distribution of rupture that they cover the entire length. So we can have partial ruptures that they are of a 40, 60, but all the way up to 80, 90 kilometers. So we can, for 90% of the fault, have an earthquake that rupture very close to the surface, but not all the way. And some of them, they go all the way to the surface. So we have a very broad spectrum of them without any clear gap between partial and complete ruptures. Another important part is that when we observe an earthquake in this type of simulations, and when we try to compare them with the observations from nature, we can see that these type of events, they can cause a subsidence in the high Himalaya. And here you can see the slip inversion and our modeling prediction, but they also can cause an uplift in the frontal part. And here you can see the map distribution of this type of events. So even in the case of Gorka earthquake, we know that the high Himalaya, and in particular Mount Everest, was subsiding for roughly 1 meter due to the earthquake. So you can see that these type of events, they can cause a redistribution of topography from the high Himalaya to the frontal part. And so this is a very important point when we think about what happened over several earthquake cycles and what caused the building of topography over millions of years. So we can run this type of simulations and try to understand what is the contribution of the different uplift rate in the different part of the faults. So here, for example, we can take 3 points on the fault, which one is located in Kathmandu Basin, so in the more frontal part of the wedge, then here in the transition zone, and the orange point in the high Himalaya. And you can see that when we move these 3 points, the vertical displacement over time is increasing. And more specifically, for the high Himalaya, you can see that interseismically, we have this positive slope where we have, when we zoom in, an uplift rate of roughly 7 millimeters per year, which seems to be consistent with the leveling data. And every time we have an earthquake, this is dropping by a certain degree, 0.5 meter, 1 meter, depending on how large is the event. However, when we take the average over several seismic cycles, we tend to have a value that is of the order of 4 to 4.2 millimeter per year, which seems to be more consistent with the uplift rate constraint from geology. And so this is clearly bringing up to a point where we want to really understand how several earthquakes or how the fault geometry itself can affect the different uplift rate from the frontal part to the deeper part, when we specifically look at the distribution of these mid-crustal ramps. And so here you can see an example of a cross-section where we have the fault with the different distribution of this décollement, where we can have also different ramps, the mid-crustal ramp. Then we can have a coupling distribution that is very high from the front all the way to the deeper part. And then we have that this is also consistent with the denudation rate and the vertical uplift. So here we have a kind of a peak of erosion rate and uplift, which seems to be consistent and affected by the presence of this mid-crustal ramp, which was responsible for the generation of this duplex structure. So we try to understand at this point also by looking at some of the GPS station, and a very interesting study from Gradet et al. In 2012 shows that there is an important feature in this type of condition, is that the peak of interseismic strain and the long term seems to coexist spatially. And in these three examples that you can see here, from more a steady state condition to a condition where instead we have out of sequence thrusting, to a condition where we have a ramp that is migrating over time, they propose this scenario, in this case, the scenario number C, where you can see that the model shows that the peak coincide between the two. And this is probably because we have an evolving system where the new ramps are created over time. And so this is the reason that can explain this sort of like match between the interseismic peak and the long-term uplift in this particular region. So we try to understand this problem by running some simple numerical simulations of an accretionary wedge, where we try to simulate the presence of a wedge that you can see here with a certain slope of the surface. We assume a certain convergence rate, and then we apply the presence of décollements. So we apply material that is weaker than the surrounding bulk, and from there we try to evolve the model over time to see what creates the condition for having the propagation of this mid-crustal ramp. And of course, this is just a very simple model that conceptually has been already used over the last 100 years. And of course, in this case, you can see that from this type of simulations, we can obtain a first order approximation of the link between surface erosion and the tectonic evolution of this type of models. Now, when we try to run some models without any erosion, so we just simply turn off the erosion process, you can see that the model shows that we have this initial internal deformation. We start to develop some ramps, but because there is no erosion, the topography grows infinitely. And because of that, we tend to have the growth of this wedge and the frontal propagation of deformation from the deeper part here all the way to the regions here where we transfer the stress because of this very high topography in this frontal part, which shows this in sequence thrust faulting. However, when we include nonlinear erosion, so an erosion that depends on the location and the slope of the topography itself, we can obtain features that are very similar to what we can observe in the Himalaya. So in this case, we have a model where we have the propagation of this mid-crustal ramp, and then because of this highly localized erosion rate, we can develop a very clear mid-crustal ramp. And most importantly, this mid-crustal ramp and the duplex can be sustained over a longer period of time. So in this case, we are assuming that the erosion is nonlinear and strongly applied in this upper part of in this back part of the wedge. So here you can see an evolution of this type of simulations where we have the composition, so the rock properties, and then here you have the logarithmic of the strain rate, and here you have the cumulative strain. And so you can see from the strain rate that we can generate this new ramp over time, roughly in the same location. So the convergence rate is pushing the ramp back, and a new one will form in front. And so this sort of like a feedback can continue for more than 8 to 10 million of years in our simulations. And we can then continuously have a creation of a new material on top of that, and continuously build this duplex on top of that, which is eroded at the surface. So when we look at the distribution of this ramp, we can take, for example, the strain distribution here within this ramp and look where is located the highest strain over time, so for roughly 11 million of years. And you can see that we have this distribution of high strain rate that is moving towards the right because of the plate rate, because of the loading rate. And then at some point we switch to a new ramp. And so this ramp is then moving over time, and then we generate a new one. So you can see that depending on the condition, this jump can be larger or smaller, but basically the range, the spatial range where we have this mid-crustal ramp is roughly located from 170 kilometers, which is roughly here, to 220. So we can have these different mid-crustal ramp that are propagating within this range. At the same time, we can see that the uplift rate tends to have an adjustment phase during the initial phase of the model. So when the model is kind of adjusting with a new structure, and so when we have this the generation of this new ramp and the duplex, at some point we reach an uplift rate which seems to stay constant over time. And similarly, the horizontal displacement is initially lower, and it tends to increase over time, especially when we create a second ramp and the duplex, and then we reach a more constant value of 18 to 20 millimeter, which seems to be more consistent with the present day value that we can see from geology and geodetic data. Finally, another important aspect is that we can use this type of simulations to then really understand the frictional properties on the fault. So based on the critical upper wedge theory, we can create the envelope of this distribution of the slope, in this case, the surface slope, which is this one in the critical upper wedge theory, and then the slope of the décollement, which is controlled by the angle beta. And so here you can see the distribution of the envelope of the two. And so in this case, you can see that this upper part, so the outer wedge, seems to have a fault friction that is roughly of 0.1. And when we move towards the inner part of the model, we tend to have a friction that is between that is roughly of 0.18. This is kind of an interesting point because it shows that over geological timescales, friction on fault, at least the apparent friction that we can measure as a strain quantity over a longer period of time, seems to be very, very low, much smaller than the typical friction that we can use to simulate fault friction and the dynamic rupture, which is more close to Byerly friction of 0.6. So this brings me to the conclusion of this presentation. And so we have seen that the geometry of the main Himalayan thrust, and in particular this mid-crustal ramp and the duplex structure, are very important features in the Himalaya because they seems to control the tectonic evolution, but also the evolution of seismicity. And so this mid-crosser ramp is, in particular in our model, highly required in order to match the interseismic displacement. And also in order to have this sort of bimodal distribution between a small and large event, this ramp and flat ramp geometry seems to be a very important component in order to have this sort of seismic behavior. And when we look at the fault friction, as we have seen before, fault friction seems to be relatively low over geological timescales, and very small variations of that could strongly affect also the recurrence time between small events, which they can be of the order of 250 years, all the way to the large ones, which can have a recurrence time of more than thousands of years. And so because of that, we have seen that this partial rupture can control the generation of a large event, because they accumulate strain, in particular in the frontal part of the fault. And so after a sequence of very small events, we can then have the condition to generate a very large earthquakes, which can propagate with large slip of more than 10 meters in the frontal part of the wedge. And with this, I'll be happy to take questions. Thank you.
Well, thank you very much, Luca. It was a super presentation on all this segmentation of the thrust and also the fundamental mechanism for thrust. Brilliant. Thank you very much. I'm sure we'll have lots of questions. So you can post your question on the chat or unmute yourself and ask your question. Anyone?
Luca, I've got a question. Thank you very much. That was a great talk. I really enjoyed it. So I've got two questions. The first one is about the intersecting coupling model. And I was wondering about the influence of the definition of your batches, which is the definition of the boundary condition on the coupling and uncoupling. Because it looks like when you've got uncoupling, it's the limit between your patches. So I was wondering if you try different patches, you've got 6, but that's probably your best model.
Yes, that's a very good point. Of course, there are definitely some parts which are that depends on the choice that we made. We try different options, and this seems to be the one that, first of all, fits the data better. So in a way, it's kind of telling us that there is some sort of different blocks that we have to consider when we take this GPS distributions. So eventually we came out with this. There are definitely some points that are very clear. For example, in the Shillong block, we have to really differentiate that, and other parts. But along the strike, we try to, first of all, have as less block as possible, because we don't want to have too many that could create a local effects. And this seems to be the one that fits better the data. And it also coincides with the regions where we have a clear step in the orientation of the fault. So when we look at the along the strike, we have this sort of like a change in the direction of the fault, and so we try to locate the blocks right there to be more consistent also with the main tectonic structures. Regarding to the initial conditions, this is definitely one. The other is more that I didn't show too many models, but we try to with this Bayesian framework to start from the condition where we assume that the distribution of our prior is with equal probability everywhere. So this allows us to not put a specific number or assuming that the coupling is low or high as a prior. And so we try to do that, and we actually observe that in some regions, this could strongly affect the final results. Why? Because the data that we use for the inversions are not helping us to discriminate whether these are high or low coupling. And that was one of the points in the different points that I tried to select on the fault to show that the data there are not strong enough to really have a good constraint on the model. And so I hope that in the future, we can have a better constraint in specific regions because we can then better constrain this coupling and distribution.
Yeah, I was wondering if the geometry of the MHD, the seismicity or topography were some of the criteria, because at the end your coupling is linked to the seismicity. But for me, the geometry is the seismicity and the geometry of the fond thrust are linked, and ultimately the topography as well. So it could be a circular argument. So that was the source of my question.
Yes, that's also a very good point, because in that specific study, we try to use a very simple fault. So the fault is planar. And we try to do that in order to have a comparison with previous studies. And when we look at the coupling distribution, at least it seems better to keep the model simple and really see whether some of the feature will come out without having any constraint on the fault geometry. So in general, this distribution of coupling is already kind of telling us this heterogeneous distribution, but we haven't tried also with a more complex fault geometry.
Thank you. That was a great answer. I do have another question. It's on the end of your talk, where you discuss the impact of erosion rate, and you've got the linear erosion rate, which is, if I picked up the right thing on the, is a function of the topography, basically. But have you looked at to integrate the fact that the erosion rate is dependent on the climate, and therefore is asymmetric with regard to the high peaks of the topography? The monsoon is coming from the south and not to the other side. So as you prograde and migrate the wedge, you also change the topography on the top on the long term, and therefore you change the erosion rate distribution across the entire range.
That's a very good point. So the distribution is strongly dependent on this erosion coefficient. And that is the one that is non-linear because it changes spatially. We assume an initial function that is spatially dependent, and then the coefficient itself depends on the slope. So that is the link between the evolution of the model. So when the wedge is moving in the front, the coefficient of erosion will also follow that sort of evolution of topography, because the steep front is moving is also moving towards the Piedmont. So that is something which we try to include. We haven't seen any big difference with that. What we found very important is to really impose a strong erosion rate within the high Himalaya region, that's sort of like that segment of the wedge. When we apply that, then we can immediately start to observe features that are much more closer to what we observe in nature, at least to a first order. Then it's a matter of modulating this parameter and trying to find the best model. But in general, the best results, we immediately obtain them as soon as we apply this nonlinear parameter of the erosion coefficient that is partially dependent from the inner wedge to the outer wedge. Okay.
There is some model, I think it's Whipple, that actually made the erosion rate function of, there is the wedge side and the back side, or the Tibet side, if you want, on the erosion rate. And have you tested that with your model?
No, I haven't. So yeah, these are the main results I obtained with this type of models. I also try to be to keep it as simple as possible. So already this nonlinear erosion law, it's strongly affecting the final results. So manipulating this law, it's kind of tricky, because you then want to find some models where the erosion rate and the uplift rate are more consistent with the observations. And that is something I've been trying to do, at least when I was looking more specifically on the duplex structure. And at least in my model, I was able to get good values with that. So
it does make sense on the west side, but as you know, that on one side you've got a high erosion rate and incision from many river, and on the other side you've got Tibet, which could be a buildup of sediment because it's not being eroded, at least in the central part of Tibet. So that's why the Whipple model, to some reason, makes sense if you look at the evolution on the long term, but the wedge propagation in your model is looking great. It makes sense.
Thank you.
By Alik. Alik, you can unmute yourself. And
yeah, thank you very much, Catherine. I enjoyed very much your talk, Luca. And first of all, comment about that. Enjoyed because it is for 25 years I am dealing with such kind of things like a geodynamic modeling and the earthquake modeling, but separate way. You know, they say assuming something instantaneous, the flow pattern, and then imposing on the seismicity, etc. But you did in one model. That's great. That's why perhaps not everybody knows about it, but really it is exciting things. I think this is for future, you know, they say going this way. But still, I have a question, and probably I didn't see this, your paper 22, I saw two names, which is Taras, who is using fluid model, and Nadia, who is using the seismic model. And this means that you merge these two models in one, correct? And
correct.
If so, my question is how you deal with time? Because it is, you know, there is a tricky thing how to jump from one time scale to another time scale. I assume that the answer exists in this paper. I assume it. But still, I am quite curious how you did these things. Because I saw you calculated something 10,000 years, which is really great. And you develop some, I mean, the earthquakes, which is a very, very short period of time. Yeah.
Yes. Well, first of all, thank you for your comment, and second, I also have a comment, and indeed, I started from geodynamics. I also work on dynamic rupture, and then now I'm working on seismic cycle to really couple tectonics and earthquake. This is one of the problems that we can see in terms of friction. So the friction that we use on plate boundaries in geodynamic models is very low. Otherwise, we don't get any plate boundary. However, dynamic rupture simulations are using a much higher friction. We have always this competing friction that we can't really explain between the long friction, the one that is the average strain over millions of years, with friction that when we can use for a single rupture event, which seems to be more close to a Byerly friction. And this is a clear example that there is kind of an inconsistency between the two, or maybe we still didn't understand completely how this friction work when we try to then extend it over a longer period of time. Regarding your questions, yes, we explained that in the 2022 paper, where we try to couple this type of simulations. So the general framework is based on the type of rheological models and governing equations that we can use in geodynamic simulations, because there is a volume-based method, and so we can solve these equations in the full domain, which is computationally very expensive, though. So I have also to highlight that point. So it's not very efficient. However, we can do that, and the system becomes also very flexible in the type of properties that we want to put spatially. Regarding your specific question about the time, we use an adapting time stepping. So the time stepping is dynamically changing between very long periods. So the time step becomes of the order of 10 to 6, 10 to 7 seconds. So of the order of years or several years. And then it goes down all the way to milliseconds when we propagate a dynamic rupture. This is, again, computationally very expensive. So the volume base plus an adaptive time stepping makes the model sometimes very slow. I hope then in the future we can really work on improving the performance of these simulations, because it started to become challenging, especially if you want to look at the future and really try to switch in 3D. But in order to simulate long and short time scales, we need a time step that is adapting dynamically from very long ones to very, very small ones when we have a dynamic rupture and we propagate, we have a dynamic wave propagation. So we reach typically time step of the order of 10⁻³ or something like that. So very small.
Is it true that your time depends on stress, for example, accumulation, or how you manage with time in terms of the to the component? Because I understand it's dynamically changed, but what components are inside to influence the time?
This is a very important point, because when we try to dynamically change that, we have to consider different criteria. Otherwise, the code will become unstable. And we can clearly see that because we have internal iterations, what we call global iterations, where the code should converge. And if the time step does not become small enough, it will start to iterate longer and longer. So we have different criteria. One of them is related to sleep, so the sliding velocity. When the sliding velocity is very small, the time step can go up, and that's fine. But when it starts to accelerate during a nucleation phase, that's the time step will start to drop very quickly. That's one, and is usually the one that is dominating the model. So that's the one that controls the real evolution. Then we have others that are controlled by the bulk velocity. Then more recently, we implemented the pore elasticity effects. And so it also depends on the pore pressure change. So how fast is this pore pressure change? Because it's then causing an instability on the fault. So we have different criteria. And at the end of the day, we always take the minimum time step that satisfies all these criteria. So because of that, the time step in some occasions can stay quite small for a long time. So when we look at a seismic cycle model, we maybe simulate thousands of years, but we spend 90% of the time, of the computational time, to resolve numerically these rupture events, which are occurring within, 20 seconds each event. So they take most of, like, 90% of the calculation at the end of the day.
Thank you very much. Great. Yeah, I'll look at the paper because I have further questions, but there's no time right now, and we'll contact you because it's quite interesting, really, what you are doing. Thank you.
We have Karim wanting to ask.
Thanks, Luca. Thanks. That was really exciting. So I have just very short questions, and one specifically with your computational framework, which is the viscoelastoplasto framework. I mean, can you consider, for instance, for the transients like slow slip, more a relation with not with the physics of the fault, but rather with your viscoplastic bulge or bulk? And this is one. And we tend always to explain things with the fault properties. And the second one is regarding the segmentations in the Himalayas. We have evidences, and it's a pity that Supriyo is not attending. We have evidences of very important lateral ramps and along the Himalayas. But my question regards a little bit more of these big features that you're describing, because they are under thrusting, right? And then if you see this, at least from the big subductions or the seafloor mapping that we have, I mean, they should be at the surface. They should be highlighted either by normal faults that should be perpendicular to the to your arc, and what is the width of these features? I mean, you expect them to be very wide, or you expect them even to change across the Himalayas? And another point, and I will stop. The evidences that we're having from seismic tomography is extremely clear, and this is something that was not very much discussed, is that there seem to be different length scales of your interseismic creeping steady state patch. Before, it seems like there is a certain length scale that starts from the duplex, from the ramp in which the earthquakes are nucleating, to another ramp. There is an evidence of another ramp to the north that hits into the big machine, which could be channel flow or whatsoever. I don't get into the debated issues in the Himalayas, but there are these length scales over which you see hundreds of kilometers along the basically north of the 1934. And this is something that I've sent you in the paper that that should appear in JGR, and another different length scale that is associated with Gorka that would imply maybe a different elastic energy storage on the long run. If you can comment on this. Thanks.
Thank you. So I'll start from the first point. Simulations of the earthquake cycle usually are within the domain of the elastic behavior. That's the best way to probably represent to a first order most of the features, and this model have been used over the last 30 years for that, and they explain a lot of different earthquake features. Now we are in a situation where we are trying to implement more physics, and one of them is could be fluids, could be including viscoelastic, viscoelastoplastic behavior, rock behavior. And when we look at more specifically on some cases, like the one that you just mentioned on slow sleep event, this could be a case where having a domain, first of all, that is a volume based, so we can calculate our strain rate as a so we don't resolve a sliding velocity on a fault, but we are actually calculating strain rate on a domain in the entire bulk. That helps us to really understand what are the strain rate conditions that allows this strain localization. And so when we look at in some regions where the deeper part of a fault, where temperature becomes important, the viscous component start to be also quite relevant. And then maybe we have the propagation of some sliding events, more like transient, that are slower than dynamic rupture. We observe also in our simulations that this localizing effect is not as strong as normal earthquakes, and this seems to be pretty obvious. So this is kind of telling us that there is that sort of like a bulk deformation that we should take into account in some specific cases. And the one of slow sleep in the deeper part with high temperature and so on, I believe is one of them, for example. So I agree with you that viscous component in those scenarios becomes quite relevant. The second about viscous part is to consider that as a process that, well, and the plastic component as well, when you try to really simulate not only the fault evolution, but also the evolution of the wedge, the topography, and so on. And so if you want to really build topography and evolve the model, you need to consider inelastic deformation and really try to quantify this inelastic deformation, because on the other hand, from interseismic coupling, it seems that this inelastic deformation is very small. But this interseismic coupling is a very small snapshot of the real picture. And so when we try to then extend that over thousands of years, millions of years, is that 10% enough to build topography? That's something that we should really try to understand. And so for that, I think this is the type of models we need in the future for this. Regarding the second point you asked, yes, I didn't go too much in detail. I was also running out of time, but I also didn't show any figure. We see some features also in terms of faulting within the Himalaya, with faults that are oriented parallel to these ancient ridges. And there seems to be transtensional or normal faulting events. So there are some features that we observe, and we discuss them in our paper, where we try to highlight the location of these faults. So it seems that this, at least in 2 out of 3 of this region, we can see some faulting that they seems to correlate with the presence of these ridges. So it would be good to really try to investigate that more in the future, and really try to understand the link between them and the possible segmentation. And And the third point, if I can I ask you to repeat the third point? So
well, the question was very, yes, it's about interseismic length scales of the steady state of the creeping patch. There is more,
yes.
I mean, we have this.
Yes. So absolutely, I've been thinking when you were explaining that before, and there are different studies explaining that. Simple model of rate and state, they also show that the coupling regions, they continuously evolve before an event. In particular, the transition from a region that is velocity weakening, so interseismically locked, to the regions where is velocity strengthening. The transition between the two regions, they typically show the coupling that is evolving before and after events. And so we have what we call it mechanical erosion of the fault. So the patch that is dynamically evolving before a rupture is changing. So in that case, studies have been proposed that maybe coupling is not steady state, but actually is evolving, particularly in this region where the stress is building up. So that's what I know so far on this. But yes, ideally, we would like to have a real observation that they show that, because what I just explained is a theoretical prediction. We don't really know whether this is something we can see also from data, or maybe we can see now, but this is kind of, as far as I know, is kind of challenging to see.
Thank you very much.
Thank you.
Okay, is there anyone wanting to ask a question? Apparently, everyone has been so impressed. They don't have so many questions. So I'm going to thank you again very, very much, Luca, because it was a brilliant presentation. And also thank everyone for coming here. And yeah, as Alec is saying, bravo. So I'll stop the recording.
So thanks. Thank you very much.